Right. Let's give a minute for people to join.
What do we have at the moment?
Can see the number 3945.
Yeah,
50.
picking up.
It's a bit less than the registration number, right?
You're 63 now. Shall we crack on?
Yeah.
Yeah.
Right. Okay. Hello, welcome. Good afternoon, for the audience tuning in from UK, and good evening for the audiences from China. Right. Okay. Can you see my screen? Fine.
Yeah.
Yeah, okay. So today is our first of 5 webinar series for Lunch and Learn. It's a joint event with the Chinese Society for Corrosion and Protection, China. And without further ado, I'm going to invite Professor Li to give a brief introduction on CSCP. Yes.
那咱
我先开始吗？啊，
那您先开始吧。
Dear President Stephen, Dr. Gao, ladies and gentlemen, good afternoon and good evening. I'm Xiaogang Li from University of Science and Technology Beijing. Thank you for your attention of the meeting. On this time of Fair of Glad Flowers, as we celebrate the fruitful harvest season, the online bilateral exchange meeting for corrosion and protection, jointly hosted by ECHO and the CSCP, is opening today. On behalf of the CSCP, I would like to extend my warmest welcome to all of you from China and UK. This meeting between China and UK marks a significant milestone in our shared journey to advance the corrosion science and engineering, and provides a platform for knowledge and ideas exchange. In this lifetime, I hope that we will spark new ideas and contribute to the corrosion and protection discipline. As we know, the rapid development of economic had led the rapid development of the disciplines of the corrosion and protection. In China, a trillion renminbi yuan size of the corrosion and protection market has been formed. This requires more and more new rules and techniques of corrosion science and protection. Thank you once again for being here. I would like to inspired and fruitful knowledge exchange. Together, we will continue to strengthen the link between the ECHO and the CSCP, and make lasting contribution to the field of the corrosion and protection. I hope that the face-to-face meeting between us will be held as soon as possible, and wish that all of you have a good health and family happiness. Thank you.
All right. Thank you, Professor Li. I would like to invite Bove next for his brief introduction.
To the screen. Using my screen.
Yes.
Yeah. Good afternoon and good evening, everyone. I am Bo Wei Zhang, the Director of International Relations in CSCP, and it is my pleasure to give a brief introduction of CSCP. Chinese Society for Corrosion and Protection is a member of China Association for Science and Technology. CSCP was founded in 1979, consists of over 8,000 individual members and 287 group members. And now we have 7 working committees and 25 specialized committees. And the branches of CSCP locate at Beijing, Shanghai, and 15 other provinces and cities. And what we do is mainly focusing on the following 5 aspects. The first is the academic communications, like the conferences. And the second one is the science popularization. And also we provide industry service like training and education consulting. We also we can issue test standards and academic awards. And at last, we have various activities for the international relations. For the international collaborations, CSCP now is a member of International Corrosion Council and World Corrosion Organization. We're also the co-founder of Asian Pacific Materials Corrosion Association. And now we have built bilateral cooperation with the organizations from 18 countries around the world, like the US, the UK, France, Singapore, and so on. Since China has a very huge market for corrosion and protection industry, like this steelmakers and shipyards, so more than 60 courses from NACE and also from ourselves are provided. And also for the cultivation of young scholars, we donate scholarships to support the students for attending the AMPP conferences and also the Eurocore conferences. And during the past 3 consecutive years, we have held 3 different international conferences. The International Congress on Materials Degradation and Protection in 2022, and the 19th Asian Pacific Corrosion Control Conference in 2023, and the 22nd International Corrosion Congress in 2024. And during the 22nd ICC, there were more than 1,020 participants from over 40 countries, and it was really a great success. It was just held in last month in Xi'an, China. Okay, that's for the brief introduction of CSCP. So for more information about us, you can refer to the official website or the official WeChat account. Thank you for your attention.
All right, thank you, Bowie. Before we begin our presentation, I'd like to note that this session is being recorded. And if you have any questions, please enter them in the Q&A box and they'll be addressed at the end of the presentation. And our presenter for today, it's Dr. Anqing Fu. Dr. Fu is the Director of Corrosion and Protection Research Center at CNPC TGRI, Tubular Goods Research Institute of China National Petroleum Corporation. He graduated with a PhD in Energy and Environment from the University of Calgary in 2010 and has 14 years of experience in corrosion and protection within the oil and gas industry. Dr. Fu specializes in electrochemical corrosion, stress corrosion cracking, corrosion failure analysis of OCTG, and R&D in anti-corrosion techniques, including inhibitors, organic metallic coatings, and clad pipe. He is also experienced in pipeline and wellbore integrity management. Dr. Fu serves on the editorial board of the Journal of Pipeline Science and Engineering, Surface Technology, Natural Gas Industry, and the Journal of Chinese Society for Corrosion and Protection. Additionally, he is an adjunct professor of IOCS, China University, Petroleum, Beijing and East China, the Northwestern Polytechnic University, Shandong University, and others. As an executive member of the Chinese Society for Corrosion and Protection and chairman of AMPP Xinjiang Club. Dr. Fu has led more than 20 projects, including those funded by the National Science Foundation of China, national key R&D projects, and CNPC R&D initiatives, and has authored 4 books, published over 80 peer-reviewed papers, and holds more than 20 authorized patents. He has also earned numerous awards and honors, including recognition as one of the 100 outstanding scientists and young scholar of China, and the 2019 CSCP Outstanding Young Scientist, and the CNPC Outstanding Young Talented Scholar. So without further ado, please join me in welcoming Dr. Fu.
Thank you very much. Can you hear me?
Yes.
Firstly, I want to say sorry to all the hosts. Sorry for the very long resume of mine. And now I think I need to share my screen. Can you see my screen?
Yes.
Okay. And good afternoon, good evening, no matter where you are. Firstly, I would like to say thank you to ACRO and CSCP. It's my great honor to have this opportunity to talk about the current research progress in oil and gas and the new energy industry from my research team, Corrosion and Protection Center of CNPC Tubular Goods Research Institute. Today's presentation is kind of all-inclusive. You can see it is a comprehensive review of my team's work in recent years. Actually, each topic like conventional oil and gas field and shale gas field, CCUS or CCS CO2, and hydrogen energy is an independent story. Today, I just very briefly introduce it due to the time limitation. Please, if you are interested to learn more details, please contact me after the meeting. Firstly, we go to the first section, the importance of the current in oil and gas industry. At the beginning, I just want to briefly introduce the 3 stages in oil and gas industry. The first one, as you know, as the oil and gas field, the upstream, and the second is the midstream, is the transmission pipeline or the long transmission pipeline, and the third is the downstream, the oil refinery. Tubular goods are the lifelines of the oil and gas industry. The tubular goods including the drill pipe, tubing, casing, tubes, and in the downhole system, as well in the gathering system, we can see the pipeline tanks, pressure vessels, and valves. Also in the long transmission pipeline system, as well as the oil refinery system. Actually, here we can see current is an interdiscipline in oil and gas industry. As we know, besides the core major like the electrochemistry and the material science or the metallic material science, many areas were also involved in this diagram I show. For example, here we, especially for the AI and the CFD, we need to include the CFD as well as the computer science in this. Also, in the oil and gas field, we need to learn more about the production oil and gas production process. For the ICC, we need to involve the mechanicals and the fracture and so on. All the current forms shown in this slide, we can find in our oil and gas field. I will show you later. Actually, it is reported over 60 failures of the tubular goods or OCTG used in oil and gas industry are related to corrosion. But especially it is reported for the gathering pipeline in China. Almost over 90% of failures related to corrosion. Cost of corrosion is more than the loss of oil and gas. I think we concern more about the safety and environmental issues. So here I just summarize 3 things related to the corrosion in the oil and gas company. The first priority should be safety and environment, and the last one is the economy. Okay, let's go to the second section. The current case studies in the conventional oil and gas field. Here, I just want to differ from the following, the shale gas. So here I use the conventional oil and gas, this term. This slide shows the typical current failures of the downhole tubing and gathering pipeline. As I mentioned earlier in the previous slide, various current types can be found in the oil and gas field. Here, I just want to emphasize all the pictures shown in this slide are collected from the field or our project instead of online or literatures. The first case is for the downhole system. The acid fracture is widely used for the enhanced oil and gas recovery or production, where it can cause the severe current to tubing as well as casing. Since you know for the acid is the solution is very acidic, so and it will cause the very severe current in the several hours or in several days. So several research undergoing in our team, new tubing material selection and acid inhibitor research and development, as well as the current evaluation facility development. And the last one is a standard for conduct the test. Since this test is very unique, so we need to develop a new standard or method to do this kind of the test. The second case is the most concerned failure in the oil and gas field, especially in high sulfur oil and gas field. In China, it's very especially in the Chuanyu basin. We have a lot of the gas field that contains very high sulfur. So it's absolutely is here the SCC is absolutely the first priority we need to consider. In the future, we need to develop the anti-SCC materials and optimize the OCTG monitoring process, as well as we need also to develop some new chemicals to reduce the SCC. The third case is the downhole tubing SCC due to the pecker fluid. This is another type of the SCC. No matter in China or in European countries or in North America, usually we use 3 types of the pecker fluid. The first one, the highly salt. The second one is a formate. The last one, it especially used in China, is phosphate. We already found a lot of sodium chromium martensite stainless steel tubing has experienced the severe SCC in the phosphate pecker fluid. Here we have found many cases in the field. Also, we have do a lot of tests in our lab. We indeed found the SCC occurred for the sodium chromium stainless steel. The first case is the tubing and the gathering pipeline erosion corrosion. No matter in downhole system or the gathering system, erosion corrosion is always a big issue. Here, I give the most commonly used in our oil and gas field industry to conduct the erosion corrosion test methods. The first one is rotating disc electrode. For this one, we cannot apply the high temperature, high pressure. It's mainly for the theoretical research is okay. The second one is impinging jet. The same thing, it cannot apply the pressure and the temperature. The third one is the fluid loop. Somehow it can apply some pressure and temperature. The last one is the CFD simulation. So currently, the lab test with high flow rate and under the high temperature and high pressure condition is still a big issue. There is no commercial or self-designed facility to do this kind of the test right now. The last case is personally, I think the most gathering pipeline current is defined as the under deposit current, that short for the UDC. Usually, the localized current is occurred at the 4 to 7 o'clock, especially at the 6 o'clock location. Inhibitors and coatings, non-metallic composite and clad pipes or lined pipes are widely used to reduce this kind of current. Actually, in China, there are many non-metallic composite pipes used in the oil and fuel gathering pipeline system, especially in Changqing oil field and the Daqing oil field and many other oil field. Since this kind of material, there is no current, but there still some degradation, especially the temperature over 80 degrees C. It can cause a big issue. Another disadvantage of the non-metallic pipe is the connection joint is a big issue. Since we usually use many kinds of the joint, but there are a lot of the leakage due to the material go inside. And another thing here I want to see is the small diameter pipe inspection technology and the quick repair techniques under high temperature, high pressure is still the big issues in the field. So, okay, let's move to the third section, the current case studies in the shale gas field. Here, I mainly talk about the microbiologically influenced current. That means the MIC. Before we go to the details of MIC in shale gas oil field, gas field, here I just want to do some briefly introduction of the shale gas production. The hydraulic fracturing is frequently used in shale gas. Usually, we use 10,000 tons of the fracture fluid and 1,000 of tons of sand inside to do the hydraulic fracturing. So this is only for one single well. You can imagine for many wells, we need to use a lot of the fluid with the sand. So here, and usually the second thing is we usually repeatedly use the fluid, repeatedly use the one batch of the fluid. So here, due to we repeatedly use these kinds of the fluid can generate a lot of bacteria. The first typical one is SRB, a sulfur reducing bacteria, and the TGB, FB, and many others. But I think the main one contribute to the current is the SRB. Here, the MIC frequently occurred no matter in the gathering system or in the downhole system. Here you can see the picture very clearly shows how the current occurred on those two systems. The current rate is prohibitively high no matter in these two systems. Here I just give an example. The 5-meter watt thick tubing was perforated within the 58 days, just less than 2 months. There was a lot of perforation. The current rate is very high. Actually, we just not found in any single well. We found many cases in the CNPC and the Sinopec shale gas wells. Our team has done a lot of failure analysis and the lab simulation of the MSE and the material evaluation and selections as well as anti-MIC steel development. Currently, our TGRI has set up a MSc lab, which is capable of conducting the SRB, FB, TGB culture and isolation and analysis, as well as the MSc test under various conditions. Based on almost 5 years research, our team proposed an ISO standard, the test method for the MSc of the oil and gas transmission pipelines. This is the first ISO standard related to the pipeline MSc test method. Actually, besides this ISO standard, we also developed several MSc related standards. For example, the test method as well as the anti-MSc materials. The next part is the corrosion in the CCUS or CCS CO2 oil displacement. Why we care the CCUS in oil and gas industry? Since it is a win-win strategy, since the CO2 was reduced and the oil was enhanced. However, the CO2 has a side effect, corrosion. In our CMPC, corrosion is considered as one of the 10 key techniques of the CCUS EOR. No matter for CO2 injection and production or for the transportation, we need tubular goods. That means pipelines, tubings, casings, which are the lifelines for the CCUS CO2 oil displacement. Here I just briefly compared the difference between conventional CO2 corrosion and the CCUS CO2 corrosion. The first one is most CO2 injection is a supercritical state, so which can induce the tubing and casing corrosion. The second one is the CO2. This injected CO2 contains the acidic impurities, which can induce the ICC. Since this kind of the gas source is mainly from the coal-fired power plants. The third one is the supercritical CO2 injection led to the low temperature. Actually, this kind of scenario we can find in our lab. If you pressurize the CO2 to our autoclave, you can see there is some ice. The temperature quickly goes down due to the CO2 injection. The last one is super CO2 induced Packer rubber failure. Based on our research, supercritical CO2 with multi impurities, which can cause corrosion, the first one. And the second one is ICC, as I mentioned earlier, stress current cracking and scaling. Since the supercritical CO2 with a lot of ions, which can lead to the scaling. The third one is the Packer rubber sealing failure, and the last one is low temperature fracture. In the following slides, I will show you the research results from our lab. The first one is the influence of the CO2 pressure on the corrosion rate. The corrosion rate is substantially increased when the CO2 reached the supercritical state. You can see from these 3 diagrams, when the CO2 reached the 20 megapascal, that means here is a supercritical state. We can see the corrosion rate, no matter for the N8 or the P110, these two kinds of the low carbon steel tubing, there is the corrosion rate increased in the supercritical state. And here we also doing some the metallurgical analysis. That means the microstructure of the corrosion products. Actually, we found that the corrosion mechanism will not change, no matter CO2 is in normal or supercritical state. why the corrosion rate is very high. That only, I think the mainly reason is because the CO2 partial pressure is pretty high. The second thing we concern is the influence of impurity is widely and deeply concerned in the CO2 transportation pipeline. Actually, we can find a lot of the publications to this research area. Our team found that if the single impurity contains the other is the first one is sulfur dioxide. The second one is hydrogen sulfide. The last one is oxygen. If the multi impurities contains other changes, the first one we can see is the oxygen plus the SOx and the hydrogen sulfide. Since we all know the CO2 has no relation to the ICC, the stress corrosion cracking. Therefore, there was few researches on the ICC in the lab research. However, acidic impurities, as I mentioned earlier, contains in the CO2 injection system, so which can induce the ICC failures. That not only in one oil field, in several oil fields, in CNPC and the Sinopec. So which is not, that means which is not an individual case. So it's very common. And we have done a lot of failure analysis for this kind of the oil field. Therefore, more attention need to be paid in the future for this kind of research. Okay. Next one, in the CO2 injection and production downhole system, packer sealing performance is very essential for the viable integrity. A supercritical CO2 played the role as a solvent. Since from the normal state to the supercritical state, it behaves as a solvent, which can dissolve the additives in the rubber, and therefore degrade the rubber in terms of the mechanical performance. Here, I need to clarify that no matter the rubber imported from other countries or made in China, most of them cannot endure the supercritical CO2. Now, we have done a lot of tests for this kind of material. And right now in China, some factories, they have developed a high performance rubber for this kind of the situation, especially for the supercritical CO2 condition. The last one is the influence of the low temperature on the tubing mechanical performance. Why we concern the low temperature situation? Since the injection of CO2 will lead to the temperature drops to as low as -20 degrees C. Based on our research, CO2 injection indeed led to the decrease of the impact energy of the tubing. Well, there was no substantial influence. So right now, we don't concern too much about this kind of scenario. So finally, I just personally summarize possible failures, including corrosion in CO2 transportation pipeline, CO2 injection tubing, as well as CO2 enhanced oil production stream. And the last one is CO2 enhanced oil gathering system. It is just based on my understanding, only for your reference. Okay, the next part is hydrogen, which is another hot topic besides the CCUS CO2 corrosion in China. As we know, hydrogen is considered as an extremely clean energy. Many infrastructures, such as pipeline, tubing for the underground hydrogen storage, liquefied hydrogen vessel, and solid hydrogen storage material. Actually, here it should be the hydrogen solid storage material, and are potentially degraded or damaged by the gaseous hydrogen. Actually, there are a huge amount of publications on the hydrogen-induced SCC, no matter in Chinese version or in English version, we can find many huge amount of the publications. However, those researches are based on the cathodic or ionic hydrogen, which is totally different, which is totally a different story for the gaseous hydrogen. Actually, my PhD supervisor, Dr. Frank Chen from University of Calgary, he has summarized the differences between the gaseous hydrogen and the cathodic hydrogen. Here, I will not to touch much details due to the time limitation. In these slides, I compared the cathodic hydrogen test facilities and the gaseous hydrogen test facilities. You can see usually there is a very classic test method is double D cell to do the cathodic hydrogen damage test, or the SSRT with the hydrogen charging. This as well as it is cathodic hydrogen charging. Currently, in our CNPC TGRI lab, we have already developed those 3 facilities. The first one is high temperature, high pressure gaseous hydrogen SSRT test. And the second one, we developed the high temperature, high pressure gaseous hydrogen permeation test. And the last one, doing the hydrogen content test, use the HTDS. That means the high definition of the thermal desorption spectrum method. We can see in this slide the hydrogen, indeed, the gaseous hydrogen indeed has the influence on the mechanical properties on the pipeline steel, no matter for the low-grade pipeline, X52, or the high-grade pipeline steel, X80. Actually, for the X80, it was commercially used in China for the very important long transmission pipeline project. But as I know, this kind of pipeline, high-grade pipeline, was not commercially used in other countries. We have also done the test for the gaseous hydrogen permeation test under the high temperature, high pressure condition, and how much hydrogen went into the pipeline steel after the test in the gaseous hydrogen environment, which was quantified by the HTDS method. Actually, those 3 facilities are not only suitable for the pipeline steel or for the tubing, it's also suitable for the alumina, titanium, stainless steels, as well as the CRAs. Okay, the 6th section is the 3 anti-current products developed by our CNPC TGRI current research team. The first one is the inhibitors. Before we go to the inhibitors, here I just want to share some problem we encountered in oil and gas field. The inhibitors are the most commonly used current protection techniques used in the oil and gas industry. Unlike the theoretical research in our lab, the physical properties are as important as the inhibition efficiency and the inhibition mechanism. Here, I give some typical example of the inhibitor physical properties problem encountered in the oil field. We can see the foaming, stratification, and pole compatibility with other additives, the pole compatibility with the MDEA, which was used for the oil and gas treatment solution, and another one is the pole solubility in the water or in oil phase. The last one is the inhibitor type miscues. This slide shows how we design and synthesize the inhibitors. Some models and some chemicals. And actually, our team have developed various types of inhibitors from the downhole acidizine inhibitor and the gasoline pipelines inhibitor for the CO2 for H2S, and also we have developed some special inhibitor for the oxygen. Since we injection a lot of gas, some of them involve the oxygen, so we need to develop the oxygen inhibitor. Also, we developed the injection water inhibitors, and for some special alloys like the titanium and the duplex stainless steel as well. And we also developed some high temperature inhibitors for the refinery. The inhibitors have been applied over 400 oil and gas wells in Changqing, Tarimou, and Qinghai oil field, and as well as in the Garrison system, we applied over 5,000 kilometers gathering pipelines. The current in downhole and the ground gathering system was greatly reduced by the inhibitor we developed, especially in the Tarimou oil field, which is the third biggest oil field in China. Another technique is the coating, especially organic epoxy coating is the popular anti-current technology used in the oil and gas field in China. Actually, there are too many coatings have already applied in oil and gas field. How to develop overall high quality coating? I think it is still a big issue. So here we develop this coating with two key factors or two key things. The first one is room temperature cooling. That means the energy saving. We don't need to the electrical heat to the high temperature. We just use the room temperature or the temperature little higher than the room temperature. So there is a lot of the energy saving. It's a kind of the low carbon coating. The second one is no solvent. It's a kind of the environmental friendly. There are no toxic chemicals evaporation during the coating fabrication or the chemical synthesis. This slide shows how we do molecular design and synthesize the epoxy coating. The coating we developed can endure the 35 megapascal CO2 and the 2 megapascal H2S under the temperature as high as 130 degrees C. Besides the paint itself, the spray process or the technology, as well as the joint connection, are very important for the coating application in field, no matter for the tubing, casing, and the pipeline, and the tanks, vessels. By now, our team has already developed the coatings for the drilling pipes and the downhole tubing and casing and the gathering pipelines, as well as tanks and vessels. Some of them have done the pilot test in Changqing and the Shengli oil field. So the last one is the line pipe or clad pipe. The line pipe is another anti-current technology used in oil and gas field in China. Usually, there are two types of the line pipe. The first one is mechanical line pipe, and the second one, metallurgical line or clad pipe. For the second one, that means there is a more or the hair bonding strength between the two layers. So the out layer is a carbon, usually is a low carbon steel to provide the strength, and in the liner usually is kind of the stainless steels to provide the current resistance. However, we have already found a lot of the mechanical line pipe failure cases, no matter in onshore oil field or offshore oil and gas field. All the failures shown here we collect from the oil and gas field. The first one is the liner blister. Since there is no bonding strength, so usually due to the pressure fabrication, so sometimes it will lead to the liner blister. And second one is the liner collapse. The third one is weld joint cracking. The last one is the weld joint corrosion. Actually, we have developed various types of the clad pipe. No matter for the carbon steel, we can see for the tubing and casing or for the pipeline. And for the liner, we developed a lot of the types of the, we can apply various types of the stainless steel. For example, martensite stainless steel and the austenite the stainless steel, or the duplex stainless steel, as well as the CRAs. And we can do many diameters from very small to the big one. Here shows the drill pipe, the tubing casing, and gathering pipe, and the bends and fittings. As well here, since it's a very complex the pipe, especially for there is a layer between two pipes. So here we need to do the fundamental research mainly for the mechanicals and the corrosion and the microstructure. We also developed the standard for the mechanical line pipe. Here we have already developed 2 ISO standards for the mechanical line pipe. We also have some pilot project for the, no matter for the pipeline. The drill pipe, the first one is the drill pipe. We have applied in the Sinopec Northwest field. The second one is the tubing and casing, which applied in the Changqing oil field. And the last one is the gathering pipeline, which is already applied in the Changqing oil field as well. So the seventh part is the challenges for the corrosion and protection in oil and gas industry. Oops. The first challenge here I want to see, the money is indeed a big problem for the oil and gas industry when we consider to select material to protect the infrastructure from corrosion. But in the aerospace or the nuclear industry, if there is some corrosion problem, sometimes we don't concern the economical concern, since that means the money is not a big problem. So I want to emphasize that for the oil and gas industry, so we need to, our first priority is the economical concern, and secondly, you have to provide the material with a very high corrosion resistance. Actually, it is very hard. The second challenge is the balance between the cost and performance in terms of the corrosion resistance. As we know, the carbon steel the price is pretty low, but it always experience corrosion in the oil and gas field, especially the corrosion environment becomes more and more harsh. If we apply the stainless steel, as I mentioned earlier, the stainless steel can provide the good corrosion resistance, but the price is usually very high. So here we need to balance, how to balance the cost and the performance. That's the second challenge we need to consider. The third one is the difference between the lab test and the field application. Sometimes we found a lot of the field corrosion perforation or very severe localized corrosion in the field. But if we do the lab simulation test, usually we cannot find the corrosion. The corrosion is very tight. Sometimes we cannot find the localized corrosion. No matter for corrosion or SCC, it's the same story. So here is the third challenge. The first challenge, how to improve the long-lasting corrosion resistance of coatings. Usually, if the coating, no matter for the organic coating or metallic coating, if the coating is intact, it's okay. But after certain times of service in the field, sometimes always we can find the localized degradation of the coating, no matter, as I mentioned, no matter for organic or metallic. So how to improve and how to evaluate or how to predict the life of these kinds of coating, I think it's a big problem. The last one, how to improve the accuracy of the remaining life prediction. Since we need to input a lot of parameters to do this kind of the prediction. But unfortunately, if you use different models and input different parameters, sometimes we will get the totally different results. So this is the last challenge I want to say. The last part is a brief introduction of our current research team. So our mission, I here just use a doctor. We are the doctor of the oil and gas facilities to protect all the infrastructure from current. Actually, we do 5 things. Why current? We need to learn why current occur and how to investigate current and how to prevent the current before it happen, and how to inspect or monitor current. And the last one, what mitigation should or measures should be done to reduce current. The morphology we use to do the engineering-based research. The first thing we do the small-scale coupon screening test in our lab. Secondly, we do the full-scale tubing coupon test for fitness for service. And last, we do the field pilot test for improvement. This is our team. Currently, right now we have 37 employees in our team, and including the 17 PhDs and the 9 research teams. For the oil and gas field current team and the pipeline current team, refinery current team, and the MSC current team, and the chemicals R&D team, and the coating R&D team, and the hydrogen material team, and the CCUS CO2 current team. The last one is the technician team. They are exclusively doing the test for all the stuffs. The research areas including the downhole tubing and casing, and the gathering and the transmission pipeline, as well as the refinery pipeline equipment. And the last one is the new areas, as I mentioned earlier, new unconventional and new energy materials. Some facilities, since for the current research, we have to use the weapons, especially for us. The first one step is autoclaves. We need all kinds of autoclaves to do the H2S CO2 current test. Recently, we just purchased 2 kinds of the autoclave from the Cortest, USA. The first one is mainly doing the very high temperature, as high as 50 degrees C, and the pressure goes to the 70 megapascal, which can input the fluid, including the H2S CO2 as well as hydrogen. The second one, we can do the temperature as low as minus 50 degrees C, which is mainly for the CCUS CO2 current test. The second part is the electrochemistry workstation. The traditional electrochemistry workstation and the micro scanning, and also for the high temperature, high pressure electrochemistry workstation. The third one is a SCC test facility. We has almost all kinds of SCC facilities for the room temperature and atmospheric pressure test. This is mainly for the standard test from the NIST, and the second one is a high temperature and high pressure test. The last one is those facilities are self-designed mainly for the full-scale tubing and the pipe test. Here is the picture shows how the full-scale tubing SCC facility looks like. We have developed this kind of the method to the AMP standard. That it is kind of the NIST standard. Another full skill test for the pipeline is the full ring ICC test facility. Actually, this kind of the method already have the ISO standard. This one for the gaseous hydrogen test facility, I have introduced this slide before, and this one, the same MSC test facility, I have already introduced in the previous slide. Okay, thank you for your attention. If you have any questions or concerns, please feel free to ask me or to email me. Thank you.
All right, thank you, Dr. Fu. We're approaching our end time at 1 p.m. So I think all the questions are going to be addressed offline. Before we wrap up the session, Steve of ICOR has a few words to say.
Thank you, Mei-Ling. I don't know.
Just going to share my screen right now. Right. Go for it, Steve.
Thank you very much. Yeah, I just want to say on behalf of everyone in the Institute, we've been really honored today to be joined by colleagues from the Chinese Society of Corrosion Protection, Professors Li and Barry. We also very much thank Dr. Fu for his excellent presentation, in which Andy provided some great experiences from the operating fields, which is very important. ICOR is the UK's leading professional organisation and dedicated to the science and engineering of corrosion control and prevention. Over the last 12 months particularly, ICOR have been working very closely with CSCP to develop collaboration in many areas of corrosion training and research. In October of this year, we visited our partners in Beijing and later participated in the 22nd International Congress in Xi'an, where we had the enormous pleasure of signing an MOU between CSCP and ICOR, as in the pictures attached. ICOR and the UK particularly has been instrumental in advancing knowledge, research and industry standards for good corrosion management. We have a membership base of scientists, engineers, academics and engineering professionals, and serve as the authoritative body for corrosion science, offering extensive support to professionals and organisations in that field. In our new joint partnership with CSCP, we intend to very much develop a much wider collaboration programme, which will include student awards, exchanges, technical events, and all types of training between us. So working together, we can achieve much more, and we very much look forward to continuing our relationship going forwards with our colleagues from CSCP. And thank you very much to everyone for joining today, which is the first of our 5 webinars presented from China, and we hope you can join us for the remaining 4. Thank you very much.
Alrighty, thank you, Steve. I'm going to end the webinar soon. I'll see you guys tomorrow for those tuning in for the second webinar. Right. Thanks.
Thank you.
Thank you all.
Thank you. That's great. Thank you very much.
Thank you.
Thank you.
Dr. Gao.
See you.
Bye, everyone.
Bye-bye.